All right, welcome everybody to Archive Dives with Oxen.ai. This is a weekly series where we dive into interesting research papers in machine learning and AI and try to tease out their key insights so you can apply them to your own work. If you're new here, welcome. Feel free to introduce yourself in the chat. There's a lot of smart people in there. We do this every Friday with the Oxen.ai community and also post them to YouTube for anyone who isn't able to attend synchronously. Some quick background on us. Oxen.ai is building a tool chain to help you collaborate and iterate on machine learning data sets like the ones used in these papers. You can think of it like Git or GitHub, but optimized for really large CSVs or millions of multimodal uh, data points. Today, we're going to be going over a reading list that I put together this week called A Road to Sora. And since the team at Openai released a technical report on Sora, but didn't actually release all of the details, I went through the references list at the bottom here and kind of picked the highest value ones that I thought would be interesting to go over, and we'll work our way through a few of those. So the one that we're doing today is diffusion transformers, which they say is the backbone of Sora in general. There's some interesting ones later in the references, like Walt, that I think would be great to go over. That would be more on the video generation side, but I think this will give us a good baseline for what is a diffusion transformer, and then we can kind of work our way up to how they can go from diffusion transformers just generating images to generating the beautiful videos that we saw with Sora. So this paper was done by teams at UC Berkeley and NYU back in March of last year. And it had some really impressive results, state of the art in image generation. And here's some examples here. Like, honestly, I know some of these might be cherry picked, but I could not tell you that that was a computer generated image. And like this bubble with the background has crazy textures. It's just really impressive that they were able to do this with the neural network. So uh, let's start with um, what is a diffusion model in general. We're going to kind of cover the basics here of each component and how they all tie these things together. So if you're not familiar with diffusion models, um, they are kind of this magical black box that can go from a set of noise and progressively denoise it into something that looks like an actual image. And I got this diagram from this great book called Generative Deep Learning. I actually got a few diagrams from there in here, so if you guys want to go check that out, that's high quality resource there. But the idea is there's kind of three steps in these diffusion models. One is you take real images crawled from the internet or wherever, and you progressively add noise to them, and they have different time steps of different amounts of noise. So you start with the real image, you make it a little noisier, you make it a little noisier, and then eventually after t time steps, you'll get something that looks like this. And then what you do is you train a neural network to progressively predict how much noise you want to subtract from this image. So if you subtract a little of the noise and then subtract a little more and then subtract a little more, you hopefully get back to the original image. And then eventually you can do some sort of mean squared error between the predicted noise and the actual noise. And that's how you train these networks. It's kind of black magic that this works at all, but what's really cool about these techniques is you don't need any actual labeled data to do any of this. You can just have a big dump of imagery and start training these diffusion models. And so traditionally, these diffusion models have had a backbone called a U-net. And the goal of this paper is to show that the inductive biases that come from a UNet and convolution and ResNets are not crucial for the performance of the diffusion models in general. You can replace these components with a transformer and have the properties of a transformer like scalability, robustness, and efficiency. So we'll start with the thing that we're replacing, just to give us all context here. A UNet kind of looks like this. You take in a noisy image in the case of a diffusion model. You downsample it, downsample it, downsample it until you go from, say you started with like a 64 by 64 by 3 image. You use your convolutions to downsample it to 32 by 32 by however many filters you want, and then 16 by 16, and then eventually 8 by 8, and maybe you end up with 8 by 8 by 128. And now that you have this really small representation, you start upsampling it back up with deconvolutional layers. And then eventually you'll get back to here. Ben, do you think you can mute that person?
What is it?
Sorry, I'm trying to find him right now. And while I look, Evan had a question as well right before we got into the architecture.
Yeah, sure, Evan.
Yeah, I immediately saying that like the inductive biases aren't necessary. I'm just wondering like transformers also have skip connections. So to me, it doesn't really feel like you're really saying anything different. You're just saying that like you don't need this unit. You can just have skip connections. Because I don't know, like do units have residual connections in them? I don't know.
Yeah, they do. So these units have residual connections here.
Okay.
And I think the inductive biases they're talking about are more the convolutions than anything.
Could you scroll for a second? It sounded like you were saying, I just want to make sure maybe I misinterpreted, if you scroll up, it sounded like you were saying that yeah, this right here, the inductive biases that come from convolution and resonance. Okay, I see. Sorry, that's my fault. I thought you were talking specifically about the skip connection.
Yeah. More the convolutional aspect of it. Cool. So they basically, what they do is in this sort of architecture where you're taking a noisy image and trying to predict the noise, they just swap out the UNet with a vision transformer, and then they get a diffusion transformer called DIT. In this paper, they kind of optimize for two different things. One is network complexity. So they measure this in terms of gigaflops, so giga floating point operations, and then sample quality, how good the images are. And they use a metric called FID, which stands for this French word that I can't pronounce, inception distance, which is basically fancy way of looking at the last layer of, in this case, they use inception v3 as like a separate network to evaluate this one. And they look at the outputs of the last layer of inception v3 when you run a real image through and when you run a generated image through. And then they compare those latent spaces and get this Frichet inception distance. And that's a good proxy for how the quality of the image is. So you'll see FID referenced a lot in this paper. In the end, they achieve state of the art on generating 256 by 256 images trained on ImageNet. And like we said, the output images look like this. A lot of these models will output the initial images in like 256 by 256 and then use a separate upsampling network to make them larger, like 512 by 512 or 128 by 128. And so the first thing they're really concerned about in this paper is network complexity. So they say that often people use parameter count to estimate the neural network architecture complexity. this paper argues that parameter count can be a poor proxy for complexity because it doesn't account for the image resolution. So obviously, the larger the image, the more compute you typically need. And whether you're using a vision transformer that uses patches or you're using convolutions, the larger it is, the more surface area it has to cover. So because of this, they look at complexity in all of their graphs in terms of gigaflops instead of pure parameter count. So that's just one thing to note as we kind of read the graphs later. Um, and so the first thing in terms of the entire architecture that we're dealing with here is they train an autoencoder as the first step. So training a diffusion model directly in pixel space can be very computationally expensive. So in this case, this is like a 64 by 64 by 3 image, but you can imagine if it was 256 by 256 by 3, that's just a lot of inputs for the vision transformer or any backbone to work with. So the first thing that they do is actually train an autoencoder to compress the image data down into a latent space. And if you're not familiar with autoencoders, it's a pretty simple concept at a high level. You kind of take an image, encode it down to a set of numbers, and then you can decode it back up to the original image. Um, and I really like this diagram from the generative AI book that talks about how you could even take these like 28 by 28 pixel fashion MNIST images and encode them directly into like two floating point numbers and plot them on a 2D chart. Now, these larger models have a larger latent space than just two numbers, but theoretically, since we can visualize 2D better, you could imagine that like if you encoded this whole data set that has pictures of pants and pictures of t-shirts and stuff like that, like all the pants would cluster over here, all the t-shirts would cluster over here, etc. And so this is a cool way of trying to take a 28 by 28 and compress it down into like a 1 by 2. And so this is the first step that they do within their model to get what they call this latent representation of the image. And once you have that, now you can train what's called a latent diffusion model, which instead of doing the diffusion on the actual images themselves, they do the diffusion on the latent space vectors of the autoencoder. So this means that you are now working in a space that's more like, in the case of this paper, they go from 256 to 2 by 256 down to like 32 by 32. And that's kind of the space they're working on, and they're noising the latent space uh, and then trying to predict the noise in the latent space rather than the noise in the images themselves. They say that they use a off-the-shelf convolutional variational autoencoder, which is actually just the same one that's used in the stable diffusion models. So that means that like when you actually look at it, the DIT is a hybrid of convnets at the top for this variational autoencoder, and then transformers in the middle. So it's not transformers all the way down, but just wanted to give you a little background for that. So looking at the full architecture together, they have this nice diagram in here, and they actually tried 3 or 4 different configurations before they got to this actual diffusion transformer block. And so this is zoomed in a little bit, but you can see right here, they take in the noised latent space. So you can imagine this is just a subset of the full model. There's actually a variational autoencoder that is sitting above here. But once you get to you go from the 256 by 256 down to the 32 by 32 by 4 noisy latent, you'll patchify it, feed it into this diffusion transformer block that we'll go over the details of, and then add some layer normalization, add a linear layer and a reshaping layer, and then the goal of this block is to predict out the noise in the latent space that was applied at that particular timestamp. So remember, there's like multiple timestamps that you're trying to denoise in a diffusion model. So they pass in the timestamp that you're trying to denoise and try to predict how much noise was at that timestamp. They also pass in the label if you have it. But that's kind of at a high level, and then we'll dive into the different experiments that they did here. So the first thing is this patchify block. So they take the 256 by 256 by 3, and just like the vision transformer, they will have something that looks like this. So this is like the 32 by 32 by 4, and they'll chop it up into patches, and then these are the input tokens to the transformer, so the latent space patches. And now the transformer kind of treats it as a sequence instead of kind of spatially like a convolution. They say that they use like the standard sine and cosine positional embeddings to encode the location of the patch, since it is now a sequence and no longer a grid. And changing the patch size has the biggest effect on the total amount of compute. So they actually experiment with a few different patch sizes, 2, 4, and 8. So you can imagine if you have, a latent space of 32 by 32, if you used a patch size of 8, then you have these 4 patches. But if you used a patch size of 4, you would have 8. And then if you use a patch size of 2, you would have 16 patches. So that just makes like a longer sequence that the transformer has to process. And therefore, they say having the patch size will at least quadruple the amount of gigaflops, which it will be important when they show the numbers later. They also note that along with the image patches themselves, they pass in additional conditional information to the stage, such as what time step of denoising we're at and the class label that they got from ImageNet. Eventually, models like Sora could take in like a full natural language string and use something like a clip model to encode that. But in this case, they're just taking the time step T and the class label, and they're embedding them kind of separately from the patches themselves and feeding all of that into the DIT block. So you can picture it like patch, 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 and then there's 2 more tokens at the end. One of the tokens is the time step, and one of the tokens is the class label. So that's what's going to be fed in to the diffusion transformer block. And they do a few variations of this to see what works best. So the first one they talk about is just the in-context conditioning that we just talked about. So appending T and C as additional tokens to the sequence. The next variation that they do on that is a cross attention block. So instead of adding T and C as additional tokens to the input sequence, they actually treat them as a separate sequence of length 2, and they add additional cross attention to that separate sequence. So if you remember, like in the original transformer paper, they have self attention that attends to the tokens. If you're doing like a a translation task where you going from English to French, you have like self-attention of the tokens here, and then you have cross-attention to the tokens in the decoder. So they say that they do experiments where they kind of have this C and T as like a separate sequence that they're doing cross-attention to, and that adds a little additional overhead um, to the model itself. The next thing they do is adaptive layer normalization. ADA line, I guess is how they would say that. And so this layer normalization is the process of making sure all the values within a layer are within a certain range. This makes it so the network is a little more stable, faster to train, and so that the values don't blow up within a network. And adaptive layer norm is this cool technique where you can actually learn additional parameters for what the mean and standard deviation are within the data as you go along, since you're not going to be able to see it all at the start. So that's why they call it adaptive, because they're learning a different additional parameters to make sure all of the values in a layer are stable. And then finally, they do this at a layer norm zero block, where I guess they add this into the residual connections to help guide how much information from the original input passes in to the next layer. And so when you look at the diagrams that we have here, the one uh, on the far right is the DIT block with just the in context conditioning. So you can see they're passing in the input tokens and the conditioning, like the time and the class label, and just feeding it through. Then they do the experiment with cross attention, where instead of concatenating the sequence, they use the multi-head attention, cross attention to look at that. And then finally, this is the final configuration that they settle on, where they add another linear layer on top of the conditioning input. They pass that in to multiple layers in here, and they have the layer normalization at these levels, as well as within these blocks. So this is kind of the final configuration that they settle on. And
Greg.
yeah,
Sorry, I have one more question from Evan.
yeah, but
Um, you were saying it's adaptive layer normalization. Um, I thought that like most layer normalizations were like adaptive. Like the only one that wasn't adaptive was RMS. Like, or sorry, not when I say adaptive, I mean with like learned parameters. So I'm just wondering like, what is this? I've never seen ADA LN like a.
I think it's just whether you're learning those parameters or you're just every time a batch comes through, you're computing just for that batch, not trying to keep like a running mean and variance.
Oh,
You know what I mean?
interesting. I guess like I thought that's how it already worked. That's interesting. But
Yeah,
I
I
guess it
think,
makes sense you could toggle it. You could either learn it or you could do it, compute it per sample.
yeah, yeah. Um, and so they do a few graphs here of like this is just with the in context learning. You can see the cross attention gives them a big bump, so lower FID is better. And then the layer norm, and then the layer norm with this special zero, I guess initialization gives them the best. So kind of 4 experiments that they ran here and settled on this final one, which totally makes sense. Um, so then the next thing that they do is look at the patch size. Um, and so let's see. Yeah, like I said, they take the pre-trained VAE that's used from Stable Diffusion. Um, this encodes it down a factor of 8, so you get the 32 by 32 by 4. Um, and so then what they do is once they have that 32 by 32 by 4, they ran a bunch of different experiments on um, scaling the patch size and scaling the size of the model in general. Um, so the model sizes that they had were anywhere from 12 layers to 28 layers, hidden size of 384 to 1,100, 6 heads to 16 heads. And you can see how many gigaflops these different configurations use in this column here. So um, these four graphs here are going from uh, the patch size 8 to the patch size 4 to the patch size 2. And you can see across every single model size configuration, making the patch size smaller improved the FID score. So that was the first super interesting takeaway here is like smaller patch size equals higher performance, but also equals more compute because you're going to have a longer sequence length to process. And then, like you would expect, keeping the patch size the same, scaling up the model size also improves the FID score. So it's kind of like they're using these two levers to pull to get the best configuration, which is the largest model with the smallest patch size, which also ends up being the most compute that you could have, which is not super surprising. But what I did find surprising was just the fact that patch size had this much of an impact and like patch size of 2 worked really well. Um, I'm curious why they didn't do patch size of 1. Maybe it was just a compute issue, but that could be an interesting experiment to run as well.
Kaiser, did you want to go with your question?
Yeah, quick question on that is, am I understanding correctly that taken to the extreme, a patch size of 1 is just like a pixel space model as opposed to a latent space model? Or is it beyond that, the patches aren't just for the latent space creation, it's doing something more?
So the patch size in this case is just the latent space. So a patch size of 1 would just be one uh, channel or one channel from the latent space here. So like a 1 by 4.
But would that, I guess that's just effectively a linear layer or something of the sort at that point. So it's
Yep.
learning something, but it is still no different than just a pixel space model that has an extra, like a, one more layer of parameters to learn.
Yes. Yeah.
Okay.
And in theory, I guess you could do this all the way in pixel space too. It's just they figured putting the transformer here is going to be more efficient than putting it at the pixel space.
Okay.
And
Yep.
there was another question in the chat while we were on this around, and maybe this will come up in applications, but what they did to kind of control and direct the generations if they used a control net specifically or something else.
Yeah, so they actually just used the class label for this one. So this was all trained on ImageNet. And so they just pass in the label Y and embed it and run it through. So if you look at the end of the paper here, they actually have a bunch of examples. And you can see that they passed in like the class label balloon, and then they got out a bunch of different variations of balloon there. So that's kind of how they condition it. Does that answer the question? Or they might pass in.
Question. But I remember for the audio files, they have this not only just patch, but also the overlap of patches, so that they can consider like the edge scenario. Does VIT or this paper consider, or I was wondering like the overlap, if how would it impact the performance and also the final FID if possible? Like, have you seen any research on that aspect?
Yeah, that's a good question. They don't mention overlap at all in this paper, but I know in the Lumiere paper that Ben presented, they did do some interesting overlapping when generating the videos themselves. Do you remember what that was called, Ben? Where they took the frames and kind of
Yeah,
overlapped them?
multi-diffusion.
Multi-diffusion. Yeah. So
Multi-diffusion. Okay,
That'd be a good thing to dig
awesome.
into there.
Thank you.
Yeah, cool. Any other questions before we keep going? Awesome. So the biggest takeaways from here is like uh, smaller models, even when trained for longer, they say eventually become compute inefficient relative to larger models trained on fewer steps. And the smaller the patch size, the better the output. So they have a nice little graphic here, and they have a bunch of these, but I zoomed into one in particular. And on this axis, it's increasing transformer size, and on this axis, it's decreasing patch size. And if you do both of those, eventually you get to this cute dog here. So pretty wild that just those two things and scaling them up can go from something super blurry here to something that looks uncannily like a dog. Um, and so they say for the final experiments, they scale this up, the XL version of the model with patch size of 2 and train it for 7 million steps and compare it to some of the other state-of-the-art diffusion models at the time. So they compared it to Big GAN and Style GAN, and just your standard latent diffusion models. I think this might be a conditional diffusion model. And you can see that the FID score is lower than all of the previous state of the arts. And the amount of compute within the inside of the network in terms of the BIT is a little more efficient, but I don't think they actually plotted gigaflops on this diagram. I thought one interesting thing just to loop back to FID, because I was a little, I didn't quite know what FID meant before I read this paper. And it is the main measure used in a lot of generative image papers. It was originally introduced in this GAN research in 2017. And they've pretty much been using the same pre-trained Inception V3 model, run the real image through and run a generated image through. And this model was just trained on ImageNet as like a classification model. They take the activations from the last pooling layer and compare them. And there's some interesting resources here if you want to see how that all works. But I think one of the main problems with that is now you're really dependent on this Inception V3 model and the data that it was trained on for your FID score. So I feel like you would just have a higher FID score if this model didn't understand what it was looking at in the image. So I thought that was an interesting takeaway that I feel like a lot of these papers are kind of brushing over. It's like if you have an image classifier model trained on ImageNet, its features are only really going to know about objects that are well represented in that data set. So like how well does would FID work if we did something like satellite images or art that's not in ImageNet? Thought that was just like a interesting thought experiment. I also thought it was interesting to dive into some of these examples at the end of the paper. They're super impressive for like landscapes and animals, which are definitely, things in ImageNet. But then when you zoom in on things like people's faces, um, or even these huskies running, definitely seems to struggle on stuff like that. It kind of makes these demonic looking faces, and definitely some interesting behaviors when you have a bunch of dogs. But when it's like a single portrait of an animal, super impressive results. So thought that was like an interesting qualitative takeaway from the paper as well. But that was pretty much it for this paper. Did we have any other questions before we dive into next
Those
week?
pictures, what patch size are they using? Because I know when you went down to the bottom right, it was like the smaller patch size. Like, is that patch size of one, or is that like, are they is there did they have to cut it off early?
Oh, these are all patch size of 2,
Okay,
and I honestly don't know why they showed the data like this, but I think these are just also images that they generated that they wanted to put in here, and they just downsampled them.
gotcha.
Yeah. And it's interesting that they put a ton, like, I don't know. It was just an interesting way of showing this, but patch size of 2. Um,
Did they say why they stopped it too? Was it just a
they did not.
computational budget thing?
Yeah, I'm guessing at some point it was just a computational limit.
Yeah. Also, Maniac in the comments kind of has the same question as me. Is like, I hadn't really heard of FID. Is it literally just comparing like L2 distance between like Inception V3? Um,
It's
like
not
I thought it was like
exactly,
is it like a learned metric? I guess that's what I'm asking.
no, it's not. It's just the differences in that layer between the synthetic and real world uh, data, and they have the equation right here, but it's not exactly L2, something a little
Okay,
fancier
so
than
you
that.
essentially you have some model and you basically use some metric to calculate the difference in activations at each layer.
At the final layer.
Okay, just the final one. And why
Yeah.
just the final one?
They say because that's like the most abstract layer that has like the highest level details about the image. But
I see.
it does
It's
seem
like
kind
right
of
before it makes a
arbitrary.
classification. It would have to have the most abstract level of detail.
Yeah. Yeah.
Is that something that's like is there like data to support that, or is that kind of like a hypothesis?
It's a good question. We might have to dive into the initial paper that proposed it. But I thought it was just an interesting metric that all of these papers are relying on, and I'm not
Yeah,
sure if it's the best one.
that's what I mean. Is like I kind of look at that and I'm like, that kind of seems like maybe it's just the bottleneck if we're like all using Inception V3 to judge how good our pictures are.
Right. Yeah.
Because Inception V3, I mean, when did that come out? I know Inception is a very old model architecture. When was V3 released? Is that
Uh,
recent or is that
no, no,
2017?
no. I mean, it was before 2017, if not
Yeah.
2017. Yeah.
So you see what I mean, though? It's like, okay,
Yeah.
we're all using 2017's finest to train our transformers.
Or to evaluate them. Yeah, yeah, totally.
Oh,
Uh,
I thought it was like propagating a gradient signal. Is it
no, this
not?
is
Okay,
just
never
a
mind.
validation
That's
metric.
fine.
Yeah,
I bet.
all good. The last thing I wanted to do before we go off and kind of just open it up for general discussion is I thought there was an interesting tweet thread by the guys that wrote this paper after Sora came out. Um, and they were talking or doing some like back of the envelope math that they think might have led to Sora. And they talked about the DIT XL2 is 5x gigaflops than the big versus the XL. Um, and they were saying, I guess back of the envelope math, maybe Sora might have around 3 billion parameters, which seems pretty small to me. And then some people, if you follow that thread, were like, maybe it's 3, maybe it's 6, but that doesn't seem super unreasonable if somebody had a large enough data set of videos. So kind of encouraging coming from the authors here, but just wanted to leave
I
that as like a note there.